Hi, my friends. Welcome back to another episode of Uncertainty and Probability Theory, the Logic of Science. We're up to episode 30, which I'm going to entitle Hypothesis Testing Stinks, Part 1. It's actually going to be Queer Uses of Probability, which is Chapter 5 out of Jaynes. That's his title. And he didn't class it per se as an object lesson in hypothesis testing, but that's what it comes down to. We're going to see at least hints at why the ordinary practice in either classical frequentist or even Bayesian statistics is a ridiculous way to carry out your business. But Jaynes did this in a very clever way. And so we're going to do this with the example of ESP. He uses the example of ESP. I'm going to use all of his numbers. The homework will be at least primarily reading the book. I have links to the book. It's on Chapter 5. First couple of sections out of Chapter 5. Not very long, but it's still going to take us a good half hour. We might even go over on this. It's only a couple of pages of material, but it's a lot. It's very dense. Now, I was having a conversation. Greg Glassman asked me, could Jaynes robot? And if you've been reading along on the book, Jaynes has been programming a robot that knows the rules of probability. And don't forget, if you're coming to this for the first time, we deduced all the rules of probability. We deduced that probability can be a number. It can take a mathematical function of a certain kind, and we deduced the shape of that function. We know that probability lives between 0 and 1 when it can be quantified. Not all probability can be quantified. We learned all these rules. We learned that the function is Bayes' theorem, and then we can go to town. We proved all kinds of other probability equations that can be deduced from that. And the robot can be trained with all of this information. And so all we have to do is feed it information and the rules to manipulate that information, and voila, we have AI, artificial intelligence. It's just a dumb robot carrying out dumb calculations, the calculations we told it to calculate, but it can do that. And so we want to think about what happens if the robot starts in a strict case of dogmatism. In a strict case of dogmatism. We're going to tell the robot, based on whatever experience, whatever evidence that we have, in which we're going to call our evidence X, for whatever past evidence that we each have about ESP. And the kind of ESP that Jaynes is mentioning is the kind, a very simple kind. Only thing we're going to consider is to be able to read minds. For instance, he notes down a number between 1 and 10 on a piece of paper, and you guess that number. Or the Zener or Zener cards. These are the star, the wavy lines, circle, square, that kind of thing. Can you guess that if somebody is sitting there looking at this, concentrating and trying to send that to you, or can you read their mind to have that kind of a thing? So we're going to tell our robot we're absolutely dubious about this, and we're dogmatic. We're going to say, given whatever information we supply the robot, the probability of ESP is 0. And then comes along data, D, from some parapsychology experiment, for instance, or from Daryl Bem at Cornell, who's famous for giving this kind of information. Well, all we have to do is use Bayes' theorem. We learned that. We don't have to use Bayes' theorem, but it's, again, I'm going to just add this little note here. We add a little d in there, if you can see that. And all we got to do is calculate this probability if we can. But we can use Bayes' theorem as an aid. Bayes' theorem is not probability. It's not a kind of probability. We're doing logical probability here. And this aid is very useful in this case, because all we want to do is, after we collect this data, we already started with knowing X. Now we're adding to it D. And we want to see what happens to our updated belief about ESP. Well, we just used Bayes' theorem. I wrote this up beforehand. So we still have the probability of ESP given X. This is our prior belief. And this is how we manipulate it. We have the probability of the data, assuming ESP is true. Then we have a denominator, which is just the probability of data itself. But don't forget, that can be busted out into the probability of the data, a function of the probability of the data when ESP is true, and a function when it's not true. But it doesn't matter what these are, because this is 0. We started believing this is 0, and once we start believing it's 0, no evidence will ever shift us, unless that evidence says unless the evidence is of the form d prime, x is false, or portions of x are false. X will be ordinarily some, enormously long set of premises, ands, ors, all kinds of things that goes into x. Unless the updated evidence is that x is false, we can't get anywhere. So we're not going to be dogmatic. We're not going to program. In science, we've often seen, this is a contingent thing. This ESP belief, ESP ability is a contingent proposition about the universe. We can't deduce that it's necessarily so. So it's a contingent belief. It may or may not be true, and we're willing to take evidence to see whether or not it's true. So Jaynes says, all right, what his experience is, he starts down at 100 dB, negative 100 dB. Now, I never did the math for dB, but it's just 10 times the log times the odds. And the odds are a one-to-one function of probability. Probability divided by 1 minus the probability, whatever we're calculating. And then we take the log 10 of the odds, and then we multiply that by 10, and that's decimals. And the reason for this is because of minus 100 dB, it turns out to be roughly 1 over 10 to the 10th. That's a very small number. It's a lot easier to use dBs in engineering for all kinds of reasons. It's a very nice thing. But so Jaynes uses dB. So when you're reading him, you'll discover that he uses this. But it doesn't make any difference. And we can immediately convert back in our minds. It's real simple. 10 times the log of the odds, and then you boom, boom, boom. And these real small numbers are so small anyway. But point of it is, he does not start off as a dogmatist or anything like this, or an ideologue. He's willing to be persuaded. And then we're going to see now what happens when we have data that should be persuasive, but isn't, in the form of hypothesis testing. Because what happens when we read all these research shows, papers and so forth, they say chocolate is going to cure heart disease. We did a hypothesis test, this kind of thing right here, and now we discovered that chocolate cures heart disease. And a week later we read another headline that says chocolate increases heart disease. They did another hypothesis test proving the opposite. So why is all that kind of a thing? So let's learn about it. So let me erase all this, and I'll give you an example. I pointed the light a different way here, and it's fine, I guess, as long as I'm standing to the side. And we'll get back to the chalkboard soon enough. But for right now, so he points to an experiment. You can go and look at the details here. It's a paper, I think, from the 50s or 60s by Soule and Bateman. And they describe what had happened. They did basically something like that Zener card thing, in which the probability of a guess given the rules, which is there's 5 cards, each with a different symbol, that kind of a thing, and no skill equals 0.2. There's 5 different cards, which we're just going to call little p, just to make it easier on ourselves. So we have no skill, and there just doesn't matter what you guess. There's no ESP involved or anything like this, and the rules say there's 5 cards and everything. We have this. So they did an experiment. They did an experiment with, and they did a lot of experiments, 37,100 different experiments, card guessing experiments. And we want to know we can calculate the probability. We can calculate the probability in doing 37,100 experiments, what the probability of no correct guesses are, what the probability of 1 correct guess are, 2. We can calculate all the way up to n. We could use the binomial. Remember, we deduced the binomial distribution earlier. And if we just want to get about roughly 60, 65%, something like this, it's a simple formula. It just turns out to be n times p plus or minus the square root of n times p times 1 minus p. This gives you about a 60, 65% chance. It depends on p, what the value of p is, and depends on n and everything, but that's a ballpark figure. About 2/3 of the observations should show up in here. And so this is a very large n, and Jaynes goes on to use something called Stirling's approximation, which gives us a normal distribution approximation to this. If you remember, we do an approximation to an approximation. Anyway, so in the experiment itself, this turns out to be, by the way, with this p and this turns out to be 7420 plus or minus about 77. That's what we would expect. A window of 60-some% chance that if we just did this, just guessing, no skill with the rules, we'd get about this many. They did the experiment, and a person got, for some reason he labels it R, 9410. They got 9,410. That's dramatically outside the window. And so that's quite different than this, which means this is, if we were to draw that binomial distribution, and here's all the numbers of successes, numbers of correct guesses, and this is the probability up here. Probability would look something like this. It's way out here, and it's a very small probability. Now, the classic hypothesis test is going to go like the following fashion, and I'm going to show you exactly how that's done. Well, no, I'm not going to show you exactly how it's done. I'm going to show you like an approximation to it. That's why I say it's not exactly the classic hypothesis test, but it's going to be something like it. All right, so let's call this, we have to explain this. In other words, how did they get to a number so large that's way out here on the tail, so to speak, where it's a very improbable result? Improbable result. It's an so what we can do, because we have this exact formula here, we can calculate the probability of this. We can calculate the probability of seeing 9,410. Okay, so let's do that. Let me erase this up here. I'm going to call this no skill HP, and I'm calling it HP, the hypothesis P. Why? Because that's what Jaynes did. It's just a label, and it means this. It means by the rules of the game, and there's no skill involved, no ESP skill involved, anything like that. That's the hypothesis P. Now, under that hypothesis, we can calculate using the binomial distribution, that we can calculate the probability, what was it, 90,410? 9,400, we can calculate 9,410 given this hypothesis. It's just another short way of writing it, and it's going to be equal to the binomial distribution n choose, what this is R equals, n choose R, p to the r, 1 minus p to the n minus r, and that equals, just plug the numbers in. Of course, these are very large numbers. It depends on the kind of computer you have and everything. But if you use the approximation, you'll get the answer. It's about 3 times 10 to the minus 139. So that's the probability of getting 9,410 hits, correct guesses, in, I think I've already forgot, I shouldn't erase all these things. N equaled 3,000, 31,000, 37,100 tests. Okay, but there are other hypotheses we might consider. How about, Jaynes says, the maximum hypothesis, the maximum, he calls it HF. Now, there's other P's that we could have used, like P equals 0.01 or P equals 0.02 or 0.03 or any of the numbers between 0 and 1. There's an infinite number of them. An infinite number. How many numbers on the continuum between 0 and 1? How many numbers are packed in there? Well, an infinite number of numbers. So that's quite a large number, a hypothesis. So we'll pick one that gives us the maximum probability. In other words, we'll test one. We'll test the probability of 1 on this. What's that probability? Well, that's a very small probability. 2. What's the probability of seeing 2 correct hits? That's a slightly higher probability, and so forth. So we'll calculate the probability. So we're going to calculate the probability of R equal 9410 given HF, which HF equaled, turns out to be 0.25. I'll get the exact number for you here because it's important. 2536, and that equaled about 0.0048. So, if the person guessing had skill, ESP skill, to the level of getting about 25% right. And that, whatever this means, whatever this HF means in terms of ESP skill, we saw that no skill equaled 0.2. And we could say that this is the highest probability we can get out of all of the possible fractions in 0 to 1. This one, 0.2536, gives us 0.0048, the highest possible probability. And you can see these two probabilities are very different. Now, what people would do in a hypothesis testing contest, this is called, we're maximizing, we could even call it, this is something like maximizing the likelihood. Likelihood is a word that sometimes means probability and sometimes doesn't mean probability. Well, we'll come to all that when we do hypothesis testing formally. But they would compare this. We could do a likelihood ratio and see that this is way out of kilter. And people would decide for this because it has a smaller probability than this. But what about the hypothesis 0.2535? Or the hypothesis 0.2537? Or 255? Or 2555? Or 2555? Or 2559? Or whatever. There's an infinite number of hypotheses. Why just pick these two? This is the real problem with hypothesis testing right here, is it limits us to these two. This one's not arbitrary. This one we can get from the rules of the game, but this one seems wholly arbitrary. We just picked it out by looking at basically taking n times p, or rather not n times p, but the number of something close to this. 37,100, and that's how we get something like this number. All right, so let's think about this. Now, if somebody gave us results like this, and they would calculate, we're not going to do it today, but they would calculate something like a p-value, and we're going to learn why these are the worst inventions in mathematics of all times, the worst mathematical invention there ever was, a p-value. But people are slaves to them. They're wee peas. They go around flashing them like they're proud of them. It's just an embarrassment in science. We need to rid science of wee p-values. But what they would do is they would point to something like this calculation I'm going to write up next. I'm going to write Bayes' theorem for this. I want to write this as this is sort of the pro-ESP hypothesis, and this HP is the no ESP hypothesis. Okay. So let's keep that in mind. And I'm going to, just because I'm lacking board space, I'm just going to write Bayes' theorem up again. I'm just going to write Bayes' theorem up here. So, and I'm going to write HF is pro-ESP. Not complete ESP. It's not a perfect level of skill. If the person had a perfect level of skill, they would have 37,100 correct guesses. And if we saw something like that, boom, 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 would we still believe? Let's find out. Let's find out. So what we really want is we want the probability that this hypothesis is true. Now that's what you don't get in hypothesis testing. In classical formal hypothesis testing, they never make statements about probabilities of hypothesis. So that's why this isn't quite hypothesis testing. We'll learn about all that another time. But we got some data, and we have our background experience, X, and we want to calculate what's our updated belief in this. Now, that's just simply Bayes' theorem. It's going to be the probability of that based on our initial guess. It's going to be the probability of data assuming that hypothesis is true. And then it's going to be, I'm going to write this all up and then I'm going to get out of the way. And it's going to be the same thing over here. It's going to be the probability of HF given X. It's going to be the probability of the data given, assuming HF is true. And then it's going to be the probability of our rival hypothesis, its prior, times the probability of the data, assuming that rival hypothesis is true, and so forth. Now, as long as we started off with a belief that that's not zero, we're not dogmatic, but it's a low number, this will be the case, given this particular data. It doesn't, the exact calculations don't matter, but it will be the case that HF, given our updated data, will be greater than the probability of HF given our initial prior beliefs or something like this. Okay? That makes sense. We can plug the numbers in, and Jaynes does, and I think I can't remember what the number is. It comes to something like 0.9999, this probability or something like this. So it looks like we should really give this a lot of belief, a lot of weight. And that's correct. That's exactly what the formula tells you to do. This probability, Jaynes starts off with about a 1 in 10 billion chance that he believes ESP is true. And then we're confronted with these results, where we see 9,000, almost 10,000 correct hits in this number of experiments. So we use a Bayes theorem, we use the binomial and all this. We can calculate every one of these numbers exactly. We come to something like really high chance that this one is now true, which means there's a very low chance that HP is true. And so we'd say, we'd have to accept, we'd have to believe that these people had ESP based on this particular equation. But yet, we still would not. Why? Well, a lot of people would. Some people would believe it, some people would not. Jaynes says he would not. I would not either, based on an experiment just like this. Because I've told people before who regularly read the blog, and I think I've done some things with you too, I practice the art of mentalism, which is magic. And magic, that is to say, like a magician, fake. I use this to fool people into thinking that I have extrasensory abilities and so forth. So I know how easy it is to fool people. And it's, in fact, too easy. Okay. So we're often, but the people will say, well, the research has showed, here's my formal calculation. They'll go through pages of this and regular hypothesis testing, and they have all this wonderful math to prove that this is now really high, or the p-value we'll come to is not the opposite of this, but everybody treats it like it is very low, and so therefore you must believe. But that's not how it works. That's not how we work. Jaynes says, these are not the only two hypotheses under consideration. This one's natural, as we decided, but HF, that's just kind of picked out of the blue. And there's all kind of other hypotheses, too. We might say, looking at this kind of stuff, 37,000 experiments, I thought maybe there was some data coding error. Or H2, what are some of the other ones that he had? Unintentional, or so the person fooled the research, or the faulty sensory leakage. We'll call it sensory leakage. That's what they call it in the ESP literature, parapsychology literature. Attell in poker, right? The guy is looking at a star, and every time he looks at a star, he goes like this in a circle. He makes a shape like that. Who knows? There could be some kind of sensory leakage. Or H3, I think the person was a man or a woman named Stewart. So Stewart cheated. Maybe used a mirror. Not all the time, maybe, but some of the time. Because, and this happened a lot in the literature, people say, yeah, they sometimes did cheat, these people who are prodigies. But you got to understand, it's a lot of pressure. I mean, who wouldn't wilt under the pressure of 37,000 these mind control or mind reading experiments? That's quite a lot. Anyway, we could have another popular one. I hope you can see this, is biased reporting of data. Like the file drawer problem, biased reporting. In other words, we got to see this data, but we didn't see all the other ones that didn't quite work out to their, to their satisfaction and so forth. So we have, when we're reading these papers and we're trying to figure out how to think about these papers, and this applies to absolutely every scientific paper you read. Anything, absolutely anything. It doesn't have to do with just ESP. We in our minds, we think of these particular things. Now, each of these would have then a prior distribution, and in our minds, not prior in the sense that we had them before we saw the experimental data, just logically prior in the equation. We went over that prior and posterior kind of nonsense before. So really what we have is we have this equation is true, but we add to this either formally or mentally, I equals 1 to whatever, we'll call it K. Let me get rid of this. We add to this all of these other possible explanations. the probability of the data given, and assuming each one of those are true, and so forth. That's what we do when we read these things, or we're skeptical. We read these papers, we say they weren't really careful about the experimental protocols. There's just any number of things that can go wrong and have gone wrong. And not just the ESP experiments, but any kind of experiment. And of course, the steward might have cheated, or of course the researchers themselves. That's not a bad one. I'll call that H5. We're hearing more and more just plain cheating from the researchers themselves. Not necessarily bias reporting, which could be an unconscious bias, but an active insertion of data that they want to work out for themselves. We saw this with the Alzheimer's trials and everything else, Alzheimer's drug trials and so forth. So cheating is also up there. So we're suspicious, and when we're looking at the cold fusion, we're often thinking these guys could not have possibly accounted for all the possible sorts of heat that are coming, and so on and so forth. We mentally supply these extra hypotheses. They become part of our Bayes theorem, our probability thinking. The interesting thing about this is if we call all of these just some kind of sensory leakage or cheating or mistakes or whatever you want to call it, the probability of the data on most of these is going to be about 1. All of these hypotheses would explain the data to a perfection almost, not all of them, but most of them. And that depends on what now it depends strongly on what our disposition. I say prior because that's the lingo, and I got to stop that. Our disposition, our thinking about these other hypotheses. And if these things are even modestly big, we'll never get this high. This probability here will remain low. It will remain low in the presence of all of these other hypotheses that we can do. And Jaynes gives an example of how to go through all those kind of a thing. And it's just amazing how this works. This is not how, if people in science had been putting their results in this form, this kind of thing would have been recognized a long time ago. But they're not. They're putting them in a bizarre form that we'll go through in a few weeks' time. It's just inexplicable when you think about it, how it lasted into this age. But if they were to put them in a form like this, these kind of things anybody can do for themselves. I don't need to read the paper. I don't need to understand all these details. I can immediately just stick this number, this big number in the denominator, and I radically change this from something that was close to 1, now that's back to 0 because of these. And the exact numbers, I don't have time to go through them. We're already up on our half hour here. They're going to be in Jaynes, and you can play with these and see. He gives the exact calculations, but this thing drops back down to nothing. And it makes sense. This is an extraordinary claim. Any kind of claim that is extraordinary, as you've heard, requires evidence. And that's what they used to say, science is self-correcting and so forth, and people would relish and even revel in critical commentary and so forth. It's not so much anymore that science is nice. We all have to get along. But it used to be like this. It isn't so much anymore. And so Jaynes gives an example of he and his student, Larry Bretthorst, he who has edited Jaynes's book, not Stove, after Jaynes died. And they came up with a way to use a logical probability in the analysis of NMR spectroscopy data, frequencies in NMR spectroscopy data, that nuclear magnetic resonance. And if you look at the frequencies of in the data of this, it gives you an idea what the underlying chemical constituents are of the things you're looking at. And they reported initial results that were much, much better. He said orders of magnitude better than the old fast Fourier transform methods. And they were not believed. They were not believed. They presented something like this first thing here with a high probability of their results, but nobody believed them. All the researchers were mentally substituting in things like this because the Fourier transforms are wonderful things. How could you possibly have beaten them so handily? So the way they got around it is they chipped away. They chipped away at each of these hypotheses. They chipped away. They gave evidence for their own data coding, for the the ways that you could do things, the actual computer code, all this kind of a thing. They chipped away, and of course now it's being used. So resistance to new techniques is not unusual, and it's explained by this kind of a thing. And so what we're going to do next time, we're going to keep going on this theme. And we're going to see, this is just wonderful analysis I just love. Now, we have two people, they start off about a belief about it, usually like a political belief or something like this, about the conduct of their favorite politician or a hated politician. And their beliefs are, they don't agree, but they're about this far apart. They both get identical information. Everybody agrees about the information. And after they receive the information, their degrees of probability are like this. Now, we've seen this happen time and time again on social media, especially at election times and so forth. How does this happen? Because the ordinary theory of Bayesian inference, we're not Bayesians, we're logical probabilists, would be that as information accumulates, everybody's beliefs should get closer and closer together until we all share the same information, one big happy harmony kind of a thing. You can see the waves of this and all kinds of implications, and I'll have things to say about it in a written lecture too. So we're going to go through that analysis. That can be analyzed in a similar way as this, and I think it's kind of amazing. I wrote I wrote one paper, I think, or two papers, kind of extending all these to how to show how to apply all this stuff to ordinary scientific discourse and so forth. So maybe we'll go over those sometime too. All right, that's quite a lot. I crammed a lot in and I left a lot out. I'm only doing a couple of pages and it's already well over 30 minutes, and I know I'm rushing through. It feels to me like I'm just running through this stuff and I'm leaving out. I got a million thoughts about everything. So if you're not following this, let me know. If you are following this, also let me know. Right now, I'm going to have, Jaynes will be the homework, and I'll have some commentary on his work. But I have the links down below. Wherever you are, or at my sites, if you're looking at this on Twitter or something like this. You can go to wmbriggs.com or wmbriggs.substack.com or look for the class, and it's all going to be there. That's it until next week. Thank you very much for listening. And again, let me know what you think.